Hello, students. I am Dr. Amanda Lowe, and I am recording this week one lecture because as we have Martin Luther King Jr. Day of Monday of week one, my Monday, Wednesday classes are missing lecture in week one. So this is a quick lecture introduction. We will do some getting to know one another in class on Wednesday for lab. For the Tuesday, Thursday classes, we'll do this Tuesday. If you want to watch the video, you're perfectly welcome to do so. So in week one, I always like to introduce my classes to myself and their classmates, an introduction to course policies and the syllabus, course procedures, and then I like to talk about why are we talking about this topic. So I'll give you an introduction to earth science and science in general. And then we'll move on into the two chapters that we're covering, which are Chapter 1, an introduction to earth science, and then Chapter 21, because the first big topic we will cover will be astronomy. So who am I? I am Dr. Amanda Lowe. I use the pronouns she, her, and hers. I don't have a problem with they, them, though. So if you forget, that's fine too. If you want to use proper address for me, please use either doctor or professor. I really don't like being called miss, and I am not a missus. So I would really prefer, if you want to be formal, use either doctor or professor. I am comfortable with you using my first name, though, if you are comfortable with it. So I am fairly casual. I am an assistant professor of earth science here at SWIC. This is now my second term here. I started in August. I have some very strange office hours. I have office hours between my two classes on Monday and Wednesday, and I will basically be staying in the classroom for that time period. So my first Monday class gets out at 1:20. My second one starts at 2 o'clock, so I will stay in the classroom between that time. I have the evening class on Monday, Wednesday as well. I will get into the classroom about 15 minutes before class starts. That time frame I think will primarily be used by the evening classes. Tuesday, Thursday, I have the morning class, and then I was supposed to have the second class of the day, but it got canceled. So I will stay in the classroom for a bit, for the 40 minutes after class, the first class, so that's the 10:20 to 11 o'clock. And then I will go home and let my dogs out, and I will be back for 45 minutes up in my actual office, which is 2201, before coming back down for the 1 o'clock class. I think I may have that wrong there. I do have that wrong there. I think I have that wrong. So I may need to review that. It's also, you can always find me by appointment. My email is amanda.lowe@swic. Or catch me before or after class, except for that evening class. I'm not going to hang around after class. Please don't try to grab me at 8:20. My specialties are geology. My bachelor's degree is in straight geological sciences. For my graduate degrees, I focused on geophysics, which is using the principles of matter to understand the earth. Specifically, I use seismology, which is looking at earthquakes and how pressure waves move through the earth. And I very specifically focused in on volcano seismology, so using seismic principles to understand volcanoes. So in class, we are going to do a bit of introduction around the rooms. I know it's a little bit awkward, but this is so that you can get to know each other. This is also so I can get my roster appropriate. So I want everyone to introduce themselves with what name they prefer to go by. And please let me know if it's different from the roster. Pronouns that you prefer, or not, I'm sorry, not prefer, your pronouns. Where are you from? Why are you here? If you're here because you need a science credit, that's totally fine. If you really are interested in the subject, that's also totally fine. And then something fun that you did over a break. I will also hand out a card. Again, please write down your name and let me know if it differs from the roster name. I will be calling roster because of needing to record attendance we have several times where you have to report the attendance, so I need to make sure everyone's here or not. Pronouns, what year you're at in the programs, what's your major, and anything that you think that I need to know. That only should go on the card that you're going to hand back in to me. And again, I will be calling out roster. I apologize if I mispronounce your name. Please just correct me. I don't like doing it, but I know I'm bad at pronouncing things. And again, I do attendance is important for lab. It's not as important for lecture in the aspect of if you can keep up, I'm fine with you missing lecture, but I do have to know attendance for the university. I have to report whether or not you're attending twice during the term. I'm primarily going to be focusing on lab for that, but I will be calling roll each day. So course policies and the syllabus. Please see the Blackboard for the syllabus and lecture slides. I will be looking over the Blackboard page with you in a moment. Please check your SWIC email and Blackboard regularly. I typically will put announcements and have it also sent as an email. If you're disruptive of class, I will ask you to leave. Please be respectful of your fellow students, especially lab. We will be very informal. It's going to be a very relaxed environment when we're doing lab because we're going to be working together, we're going to be moving around, but please be respectful. We're going to cover some topics that could be considered controversial. Specifically, we'll be looking at climate change. I present the views that are supported by scientific research and accepted by the majority of the scientific community. If you want to have a discussion about it, bring your scientifically supported research and we can have a discussion. So again, you're free to have those personal opinions that disagree with the course content, but you will be expected to learn these concepts that are supported by scientific research. And again, if you want to have a discussion about it, bring your peer-reviewed, supported research, and we can have that discussion. Your grade is going to be coming from several different activities. One of them will be called, quote, participation. Participation is on the Pearson website. It is the reading quizzes. So they have the name RQXX, RQ01, RQ21 will be the two for this week. And this will be 10% of your grade. There will be a weekly quiz on Blackboard that is going to be 15% of your grade. Those are questions that I put together. So most everything starts Monday and closes end of day Sunday. That all of the online work is due at the end of the day Sunday for the week. You're not timed on this stuff. For the Blackboard quizzes, you only get one shot at them, but you can return to it as often as necessary until you submit it. Just please do remember to submit them. The reading quizzes are also not timed, and you it will tell you when you open it what the rules are for it, but you have multiple shots at it, basically. You also will have online mastering assignments through the Pearson website. They will be 15% of your grade as well, and they will be due end of the day Sunday. These are going to be longer. Again, you will have multiple shots at them, and you have multiple shots at the questions within them. When you open the Pearson assignments, it will tell you what the rules are for the assignments. Exams will be 40% of your grade. They will be given during class time, so we will not have a lab in the week with exams. You'll have an exam instead. If you have accommodations, please talk to me about them. It's best if you get them submitted as soon as possible, but I need at least 2 days before the exam so that I can get the exams over to the testing center or to the DAC, and that you can get your schedule. I will tell you that I will not prevent you if you have an accommodation from using that accommodation, but there will be tests where taking it by yourself in the testing center may be not as beneficial as taking it in the classroom. We will, on some of these exams, have the ability to work together for parts of the exams. So I'll talk more about that when we get closer to the actual exams, but I just want to warn you about that. Late work is not accepted, except for the Pearson. The Pearson does allow you to turn things in late. Blackboard, if you miss those quizzes, you miss those quizzes. Labs, you have a week to do them. If you miss them, you miss them. You get to drop your 2 lowest quiz scores, the Blackboard quizzes. So that is the late policy. You also get to drop your lowest exam score. So if you decide at the end of the class that you're happy with your grade, you don't have to take the final. Laboratory exercises should be completed mostly during the lab period. They're due by the beginning of the next lab or exam in the case of exam weeks. So that gives you basically a week. You should get them mostly done during that lab period though. And again, they're not going to be accepted late. You have a week to get them done. If you don't get them all done, turn in what you do have done though. The lab will most weeks be the second meeting, so either Wednesday or Thursday. Weeks that have an exam will have no laboratory exercise. You have to pass the lab, so get a 60% or greater on the lab exercises to pass the course. Labs are 20% of your final grade. If you miss more than 3 labs with unexcused absences, you will be dropped from the course. So if you don't contact me saying that you're going to miss lab, you will end up being dropped from the course. If you have an excused absence, I will give you access to laboratory exercise material during week 16 for makeup. You have to arrange this. You can do this for one laboratory. You have to arrange this with me no later than week 15. So you need to tell me that we did have an excused absence. Here's the material. If you're going to miss lab, let me know as soon as you know you're going to miss it. Sometimes we can get ahead of this. It depends on what the situation is, but you need to talk to me about it. Don't just miss lab and then expect to be able to make it up 2 or 3 weeks down the road. I need to know, if you just don't show up at lab, I'm not going to work with you on it. Let me know if you're missing lab. So your deliverables, you will have a weekly lab that's due by the next lab, so you can turn it in when you're finished it at the lab period. You can turn it in at the next class. You can turn it in office hours, or you can wait until the beginning of lab and turn it in at the beginning of lab. Again, if there's an exam, it's at the beginning of the exam. The weekly quiz on Blackboard will be due end of the day Sunday. 14 of the 16 of those are going to count towards your grade. The weekly mastering assignments will be due end of day Sunday. The weekly mastering reading quizzes, which is the participation, will be due end of day Sunday. And then there will be exams. So there are 4 exams. The best 3 grades will count. The 4th exam is during finals week, and it is comprehensive. So it's going to be harder. So Sunday you have 3 different types of online material. If we're covering more than one chapter, you will have more than one reading quiz. So be aware of that. Your Blackboard shell will tell you what you have due. Grades. Exams, 40% of your grade. Best 3 of 4. Lab exercises are 20% of your grade. Mastering online exercises are 15%. Online quizzes, those are the Blackboard quizzes, which you have best 14 of 16, are 15%. And then participation, which is the reading quizzes, are 10%. You will have 4 columns in your Blackboard gradebook. One of them will say running total, I believe is how I have it phrased. Let me actually see if I can. Let me pause this for a second so I can double check exactly how I have it phrased. Okay, I am back now. So I have this is what I made up at the beginning of last term. I didn't change the text on here, but let me actually go to the Blackboard page so you can see this. So this is a student preview. So this is what yours would look like. Blackboard page. I am currently in my grades. So my grades, at the top you will have 4 weighted columns. So you will have weighted grade. And there is a description for each of these and grading criteria. And running percentage. Weighted grade and running percentage match each other. So this is the grade you are on track to receive, assuming you continue earning similar grades throughout the term. This grade only takes into account items that have grades submitted. All other items are ignored. So weighted grade will give you a letter grade. Running percentage will give you a percentage. So this grade is assuming you do similar work to what you've currently done. That's what you would be receiving. It's ignoring anything you haven't done yet. The other 2 go together. Non-running grade and non-running percentage. This is your grade at the exact moment. This grade will start as an F for everyone because anything not submitted is counted as 0. You cannot do worse than this grade. This grade will go up throughout the term. So when you get to the end of the term, this non-running grade, non-running percentage is the absolute lowest you can get in the course at any given time, because anything that hasn't been graded is a 0. So everyone right now has an F in this one and a 0%. This will go up throughout the term. So these two will start coming together. When you get to the end of the term, when you start to try to figure out where you're at, you're going to want to pay a lot of attention to this non-running grade. All right. The grades are the normal 90, 80, 70, 60. I round normal, and it's set up, the Blackboard is set up that an 89.5 rounds up to a 90. Blackboard, okay. Instead of going through all of these, I am going to go, well, I guess I can go into the actual Blackboard shell at this point. So, where's my Blackboard? Here's my Blackboard. So Blackboard, you will have announcements. The first announcement is talking about Pearson. So you should have an access code. So you should do this first part. That you go to Pearson. Pearson is not listed on here. Oh my, I have to add that. I'm not sure why Pearson's not listed on here. That's interesting. I need to add that link. So you will go to Pearson. There should be a link over here that is currently missing. I will add that back in. And so you can also get to it by going to any of these. And anyway, so it will ask you to register. You should have an access code that came with your lab manual, and you will input that. If you haven't had a chance to get your lab manual yet, you can do temporary access for 14 days until you get your lab manual, and then enter the access code. Announcements will show up here. The only other announcement currently is about lecture slides. So lecture slides if you need accessible lecture slides, go into the actual PowerPoints place on the menu here, because this is where the PDFs actually live that you can use the alternative formats. In course content, I will have a link to the PowerPoints, but it's a link, so you don't have the alternative formats here. So might want to make that note. Syllabus, okay. So your syllabus is syllabus. So the syllabus is there. Course content, I will have a weekly folder that will pop up during the week for next week. So in the weekly folder, I will have, this first week I have a link to this registering with Pearson, how to do that. Your weekly quiz will be here. So this will link you to your Blackboard quiz. Excuse me. You have to go to Pearson to go to the Pearson assignments. So this is the Blackboard quiz. I also will have a link to the slides. I will have just a list of what mastering assignments you need to do on the Pearson site. So in week 1, we have Reading Quiz 01, Introduction to Mastering Geology, Reading Quiz 21, and Mastering Chapter 21. So I actually do have the links to those items. So Reading Quiz 01, these will take you directly to the Pearson site to do these things. The other thing in here will be the pre-lab video, which is just a little introduction to what we're going to be doing in lab, and I will show that at the end of the lecture most times. So that's just showing content again. I do have Scotty on here, so Scotty is showing up on here, and I will fix these links so that Pearson actually shows up. It will show up here. So Scotty is the student success online tutoring. There is also online tutoring here. That's not the Scotty. It's a different online tutoring. Blackboard help is on here. I do have on here student notes. So if you are willing to share your notes with other students, please do use this note submission that you can upload PDFs or Word documents of your notes, and then I will post them here for other students if they want to access them. So this is just completely voluntary if you're willing to do that. Um, and if you do upload notes, please let me know. Also, please say in the file name what week or what chapters your notes are for. You will have my grades. So this is where you have your grades. And then there's a link for email. Please only send email to my SWIC email address. If you send an internal message, I probably won't see it. I do also have interesting links. So these are different web links of various things. Mostly, this is albums from when I went to Antarctica and the South Pole at the moment. But anything interesting that I find throughout the term, I will put here. And I believe that is most of what I want to go over on the website. So you will have this navigation on the side. Labs will have, basically course content will take you everywhere. It will have a weekly folder that has all the information for that week in it. If you just want to go straight to one of the lab videos, you can go into labs and there will be the weekly folder for each lab, and any other files. Quizzes, again, will have that's where the actual quizzes will be, but there will be a link in your weekly course file. PowerPoints are where the PowerPoints again lives. The course content folders only have a link. Pearson will be a shortcut to the Pearson content, which I will fix. Scotty, again, is the online tools. I haven't actually set up the calendar, so you can add to your own calendar. And then Blackboard Help is if you need help with actual Blackboard. Expectations. I do have the expectation that we are respectful of other people's opinions and experiences. So please do not share things that are shared in this classroom outside of the classroom unless you're trying to tell someone about a cool topic that we discussed. But if someone shares a personal story, please keep that private. I have a zero tolerance policy for disrespectful comments, racism, or other forms of discrimination, bullying, etc. And I need to add that I am safe zone trained. So I like to apply the safe zone principles to anyone who feels marginalized, not just people from the LGBTQ plus community. So my classroom is I strive to make it as safe as possible for all my students. If you get behind or have problems in this class, tell me. I can't help you if you come to me in week 16 with problems. The second you start getting behind, let me know. Talk to me. I will work with you. If you don't come to me, there's nothing I can do about it. So please let me know if you're having problems. Note, there is a new withdrawal policy. The date for withdrawal to pay attention to for this class is March 31st. The responsibility with this new withdrawal policy is on you to withdraw if you feel that you should. After the final withdrawal date, I can't withdraw you, and it's a pain. So make sure that if you think you may need to withdraw, that around March 31st that you're doing it. So we will do this in person, and possibly in person. But please think about how you want to be treated this term. And so we can talk about this a little bit during lab, when you're working with your lab partners, but think about what type of things you would like to see in this classroom for how we treat each other. And then I have a wiki on your Blackboard page under wikis. That's the classroom's expectations. So you go into this classroom expectations, hit edit wiki content, and then you can add to this. So for example, let's add, please silence all mobile devices. And then we would hit submit. And so we can have this be a living document. And again, we will talk a little bit about this during lab on Wednesday. All right, so now let's go into some of the topics. What are we actually doing here? So, this is a science class. What is science? Science is a method to produce systematic and repeatable observations that test models or explanations of natural phenomenon. Science is a process. It is not just a static thing. It is constantly changing, constantly evolving. It's a method, it's a process. So we are asking and answering questions about our physical or natural universe. So it has to be observable. So we can quantify it in some way. So time, distance, temperature, something. We have numbers. It has to be repeatable. So we have to be able to redo the same thing multiple times. And other people have to be able to redo it and get the same or similar results. Science is going to be falsifiable. This means that the question has to be able to be tested and proven wrong. Like we have to be able to say our initial thought was wrong. Our initial belief that we were testing is wrong. So we start off with a question. And then we will have some preliminary experiments, observation, and data collection that is based on this question. This will help us form a hypothesis. A hypothesis is a reasonable explanation that fits the observed data, the observed facts, and is likely to account for any future observations. So we have to be able to test the hypothesis, and it can be rejected, but it can never be accepted. So we have to be able to test our hypothesis and see, did we disprove our hypothesis? If we did, then we have to refine it. So we do additional testing. Once we get to the point where our hypothesis is fairly well tested, that we think we account for most every observation that's going to come forward, that's when we can say that our hypothesis has been elevated into a theory. So a theory is an extremely well tested hypothesis. So it's a hypothesis that withstands repeated testing and is supported by an overwhelming amount of evidence. They are subject to change when we have new observations. So in geology, we've had a lot of theories that have gotten changed as we learn new things. If we go far enough, the theory can become a quote law, and law is in parentheses. So a law is something that completely describes a specific relationship or phenomenon without any exception for a range of conditions. So it is something that is gone beyond being an explanation, that it's a statement of fact, essentially. So we go through this continuous retesting and reevaluating, and even when we haven't completely disproved our hypothesis, maybe we have an observation that's led us to a way to make our hypothesis better. So we will go through this many, many times. Sometimes as we're testing, we have a completely new question come up that we then need to address. So science is this process. It's a method. We are constantly doing new iterations. So in science, we strive for a thing called parsimony. So this is the idea of Occam's razor. So plurality should not be posited without necessity. Basically, don't make it more complicated than it needs to be. The simplest explanation is most likely to be true. So we don't need to add things that are unnecessary. So an example of this is if I am visiting my family and I had a piece of cake in the fridge that I was waiting to eat, and I go to eat it and it's gone. There are various things that could have happened. My roommate or my someone in my family could have eaten the cake. I don't have a cat, I have dogs. So my dog managed to open the fridge and eat the cake. If it's chocolate cake, that's a bad thing. And an alien could have come in and eat the cake. Maybe a dinosaur came in and ate the cake. One of these is more parsimonious than the others. One of these is a much more elegant, simple solution, and that is the idea that a roommate, a person, opened the fridge door and stole the cake, um, which is what actually happens in my family. My dogs are smart, but they don't have thumbs. So, one more time, science is a process. Hypotheses are explanations. They try to take into account what we have observed and what we may observe in the future. A theory will be a well substantiated explanation or hypothesis. It is to the point where we are taking into account every possible observation we've had or could have. A law is a theory that no longer gives an actual explanation, it just explains relationships. So we are always looking for the parsimonious explanation. The simplest thing is often the true thing. We don't need to make it more complicated than it needs to be. So Earth science. Earth science is essentially the collective sciences that seek to understand Earth and its neighbors in space. So Earth is our planet, but Earth science includes other planets as well. So this includes many fields. Geology. Geology is the study of Earth, the study of our planet. Oceanography is the study of oceans. Meteorology is the study of weather phenomenon. Astronomy is the study of extraterrestrial, outside the Earth, bodies. So we are going to start with astronomy in this class. That is going to be the first thing that we look at as a big topic. So there are different ways of looking at Earth science. You will see different names of things. So environmental science is sometimes used in the same way as Earth science. In this country, environmental science does sometimes get a bad reputation. It's often looked at as a soft science. That's not true in other countries. Geoscience is kind of a general, broader term as well. It's often used in the same way as Earth science. The one I like a lot is Earth system science. This kind of takes everything into account. And then we also talk about the different spheres, so Earth spheres. And we use different spheres a lot in Earth science. So there are different words that essentially mean the same thing. And there are many more than just these. So when we're looking at these spheres, they're useful because, well, the Earth is spherical, and many of our things that we're going to be looking at actually are layers. And so you can think of it as, circles, spheres, 3D circles. So we have what's called the hydrosphere, which is basically the water on the planet. We have the atmosphere, which is the gas layer around the planet. We have the biosphere, which is all of the life on the planet. It tends to be mostly on the surface of the planet. And we have the geosphere, which is all of the planet itself. It is the layers of the planet. So you can imagine how these are spheres, they're shells around the planet. Earth science is very big in both size and time. So if we think about it, the planet, Earth, it's big compared to us. Our planet's actually pretty small when you think about it in the solar system. It's tiny compared to the gas giants like Jupiter, but it's minuscule compared to the sun, which is our star. Our star is actually a mid-range star compared to other stars in the universe. Our solar system is within a galaxy. Our galaxy is within the universe. So Earth science takes into account a lot of space, but also a lot of time. So if we condense down the history of the Earth into a calendar year, the first thing that happens is the Earth is formed. This is about 4.56 billion years ago. GA stands for billion years ago. The oldest known rocks we have are about 4 billion years. So if we're doing this over the course, condensing that 4.56 billion years into one calendar year, that means the oldest rocks on the planet show up in February. The first single cell life is 3.9 billion years. So I just want to point out 4.03 billion years to 3.9 billion years is more than a month apart in this. Billion years are a lot of time. The first multicellular life is about 1 billion years. So this is the second half of this year is when we get to like more complex life. And this is still pretty simple life, all right? The first time we're having hard parts, so this is actual exoskeletons and, not just squishy bits, is about 540 million years ago, which happens in November if we look at this 4.56 as a year. The first land plants are about 440 million years, so now we're in December. So this is the first time we get out of the oceans, all right? Dinosaurs are about 230 million years ago. So this is towards the end of December, all right? The end of the dinosaurs is in the last week of December. This is about 66 million years ago. So the end of the dinosaurs is in the last week of December. All right, we're talking about a lot of time when we're talking about our planet. Homo, which is our overall family, shows up towards the end of the last day of December. Homo sapiens is in like the last minute of this year. And Homo sapiens we're Homo sapiens sapiens. So we're talking an immense amount of time when we're talking about Earth science. If we're talking about the history of the planet, an immense amount of time. We're going to be looking at the geologic time scale throughout or in this term. But we're talking about very, very long time periods. So how did everything start? So we start off with the Big Bang about 13.7 billion years ago. So this is the start of the universe. That the birth of the universe began as a solar nebula. Dust and gases collapsed down. This all started with hydrogen. So hydrogen is 1 on the atomic scale. Two hydrogens combine together to be helium, and then from there we get to the rest of the elements. Nebular theory is this idea that objects evolved from these clouds, so nebular clouds, to disks that rotated. So these disks of dust and debris would flatten down and rotate, and as they rotate, material starts to pull together from gravitational pulls. So you start to have these rings of material that will continue to condense down into individual objects. So the first objects that form will be planetesimals. These are the cores of our future planets. Gravity will organize the various objects in a given solar system into orderly orbits. So you will have the smaller objects tend to be closer to the star. The larger objects tend to be further out from the star. Earth forms about 4.54 billion years ago. So Earth is going to be younger. Or rather, Earth's about the same age as our solar system, is slightly younger than the actual solar system. So our solar system formed quite a bit after the universe started. So I'm going to show a NASA video now. Hopefully I can turn off my sound so that you won't hear me. I'm not sure that worked. So there should be a way I can turn off my sound, and I'm not sure how to do that. But
the Milky Way, home to billions of stars, rising and setting over billions of worlds, including our own. In this vast expanse, how did our sun, the Earth, and the planets come to be? In recent decades, our understanding of the solar system's evolution has greatly improved, but deep questions remain. To answer those questions, astronomers are preparing to visit someplace very small. Asteroid Bennu. A lump of rock and organic material, the early building blocks of the solar system, of Earth, of us. Bennu is a time capsule, and its journey takes us way, way back, 4.5 billion years. The raw ingredients of Bennu and our solar system originated in a stellar nursery, a vast cloud of hydrogen, helium, and dust. Our own sun doesn't yet exist. Nearby are hot stars like this one, quickly burning up its fuel and destroying itself in a colossal explosion called a supernova. The explosion destabilizes our cloud, causing it to collapse. In the geologic blink of an eye, 100,000 years, gravity and angular momentum flatten the cloud into a swirling disk. In the center, where molecules crash together tightest, a protostar revs up to incredible pressures and temperatures. Deep within the disk, clumps of dust not much larger than a grain of wheat are flash heated into droplets of molten rock, called chondrules. The source of this heat remains a mystery. Chondrules are destined to become the building blocks of the solar system. Coaxed by gravity and turbulence, the chondrules clump. They grow into the first asteroids, into mountains, into planets. The asteroids are rubble piles of rock, metal, ice, and organics. This large asteroid is the parent body of Bennu, a protoplanet whose size we can only guess. Closer to the protostar, a planet begins to form. And then, dawn in the solar system. The protostar undergoes fusion and ignites, revealing our sun. But the solar system is far from finished. Jupiter most likely forms near its outer edge, but just 500 million years after the sun ignites, some believe that it slowly moves inward. Its massive gravity ripples the asteroid belt, disrupting countless asteroids and comets, flinging them toward the sun. They rain down on the inner planets, hammering and remelting large portions of their crust. Did these impacts also deliver organics and water, key ingredients for life? Back in the asteroid belt, Bennu's parent body is lucky. It survives this period of heavy bombardment. The solar system cools and calms. Jupiter and its many moons assume the orbits that we see today. Billions of years of quiet follow, more or less. Then a billion years ago, one theory suggests a collision shatters the protoplanet. Some of the debris loosely coalesces into a new, smaller body, Bennu. But Bennu will not stay in place. Dull, non-reflective, it slowly migrates toward the sun. Solar heating turns its warm side into a low-intensity thruster. Through millions of years, Bennu's orbit gradually tightens until it interacts with Saturn's gravity, altering its trajectory and hurling it into the inner solar system. Close encounters with Earth and Venus follow. Their gravitational tugs may have repeatedly stretched and reformed Bennu, turning it inside out and pulling off loose material. As a result, it has no satellites of its own, until now. Today, NASA is sending a spacecraft called OSIRIS-REx to explore Bennu and retrieve a sample. Why? Bennu has survived its long journey and settled into a near-Earth orbit, bringing its secrets within our reach. Now it is ready to teach us more about the solar system's history, its formation, its evolution, and our own place among the stars.
I apologize for if you heard me breathing over there or moving things around, or if you heard my dog come in. Luckily, she doesn't have her collar on at the moment, so it wasn't making jingle noises. I'm recording this with a screen capture software that doesn't have an easy way to mute my microphone, so apologies. So, astronomy is the study of the stars, the study of bodies outside the Earth itself. All civilizations look to the stars. It's just part of human nature. Much of, quote, modern astronomy comes down from ancient Greeks and Middle Ages Europe. I don't like the fact that our textbook only looks at the Greeks and Middle Ages in Europe. There is significant astronomical study in other cultures as well. So I'm not going to talk so much about the people. You will need to read that for your reading quizzes and your mastering homework, but I'm not going to go over the individual people because I feel it's rather European centric in our textbook. But there are some things that are common to look at. So, the shape of the Earth. So, one of the things to look at is that during eclipses, the shadow is rounded. So, that indicates that the Earth isn't flat, that the Earth is spherical. And we can see that. If we see a shadow and the shadow is not flat, that implies that the Earth itself is not flat. We can also estimate the size of the Earth. Many of these early workers were able to estimate the size of the Earth. So, using geometry of known locations and heights, they came very close to modern values for the size of the Earth, and that's rather impressive. How the Earth is organized is one of the things that had some issues in early studies. So, there are two different ways to look at how the universe not really the universe, how the galaxy, the solar system is organized. Basically, you can think about we're the center or we're not the center. So, geocentric is the Earth is the center of everything. Everything else revolves around us. And unfortunately, that's the way many people went. They thought we're the center of everything. Turns out we're not the center of everything. Heliocentric is the sun is the center. So the sun is the center of our solar system. Our solar system orbits around another object that's going to be the center. So we're orbiting something else. That turns out to be the correct way of organizing things. So where did some of these early workers go wrong? The Ptolemaic system is a geocentric modern model of the universe. So perfect circles is the other problem with the system. So one, the Earth is not the center of everything. Two, it's not. We don't actually have perfect circles in our astronomical bodies. So the Earth isn't a perfect sphere, and we don't orbit things in perfect circles. So we also had issues with retrograde motion. So retrograde motion is where we observe things going backwards, and that's just because we are orbiting the sun, other objects are orbiting us, and depending on how fast things orbit, or other objects aren't orbiting us, only the moon orbits us. But for example, in this image, we see that Mars is orbiting slightly outside our Earth's orbit. And so at times, because of the orientation of Mars to Earth, it appears that Mars is going backwards, that we have what's called retrograde motion. And it's because of the different reference frame that we're all orbiting this central point, but we're doing it at different rates and different distances. This idea of retrograde motion is actually fixed when we understand that we're not orbiting at perfect circles, that our orbits are actually ellipses, that the orbits are slightly squashed, and that actually fixes this idea of backward motion. They're not all in the exact plane around the sun either, and that is another important thing. So nothing is perfect in our system. The shape of these orbits and locations is going to be controlled by gravitational force and inertia. So the relative attraction between the sun and other objects is going to control how far away those objects will move from the sun. The second problem that was a major issue with many of these early theories, or not theories, even early hypotheses, is that in many cases they were trying to fit with religious teachings, various religious teachings, and that's never going to work out right. So, there were some very odd things that were proposed in order to explain things with religious, um, you know, in the religious sense. So, what do we see in the sky? Um, One of the things we see in the sky are constellations. All cultures look to the sky and see patterns, and they see them in different ways. So, the constellations are those patterns. So, a constellation is a pattern of various stars that looks like a shape to someone. I personally have a hard time seeing most constellations except for the dippers. I can see the dippers and Orion's belt, but just the belt. Um, there are different names for these groups of stars. So, for example, Orion is the archer, and the belt, which is the only thing I can see in him, is the stars that are diagonal across the center section. The stars appear to remain fixed relative to each other while they're moving across the sky. That is due to the fact that these stars are so far away, and our planet is actually rotating. So we see them moving across the sky because of the rotation of the planet. These stars are not actually close to each other. They just look close to each other in our view. We can't really see the distance to them other than the strength of the light coming. So these stars, in a given constellation, they may be, some of them are significantly further away than other ones. Um, so it's all about our frame of reference to it. Polaris, or the North Star, is a particularly bright star, so fairly close, that is located near the North Celestial Pole, um, or the reference point where our planet is rotating around. So if you extend the rotational axis out, the stars appear to rotate around the Earth's rotational axis. Polaris is a star that just happens to be very near to that point, so it appears fixed in the northern hemisphere. And it's useful for navigating for that reason because it is fixed, and we call that the North Star. So what we see in the night sky and the day sky is going to be dependent on movements of the sun, earth, and the moon. So the earth spins on a daily variation. It is rotating on um, a daily cycle. It also is orbiting the sun on a yearly cycle. So the rotation or the spin daily is going to be day versus night. So are we facing the sun or are we facing away from the sun? The orbit, it takes a year to orbit. That is going to be the seasons. So, and we will talk more about this when we look at patterns in weather later on. But how the sun, or I'm sorry, how the Earth moves about the sun is going to determine the seasons. We have opposite seasons between our two hemispheres because, excuse me, the rotational axis of the Earth is actually tilted compared to the plane that the orbit is. And that tilt is 23.5 degrees. And so we have opposite seasons in the different hemispheres. So when we're currently in the boreal winter, which is the austral summer. So Australia is having summer right now while we're having winter. We will talk more about this again later on in the term. Another aspect of our orbital cycles are called Milankovitch cycles. So Milankovitch cycles are long period variation in Earth's orbit, and there are 3 of them, and they impact climate. Again, we will talk about this a little bit more later on the term. So we have one called eccentricity. Eccentricity is how much of an ellipse the orbit is. So is it more circular or very strongly elliptical? And that's on a frequency of about 100,000 years. So this basically determines how close to the sun we are. Obliquity is the tilt of the axis. It's on a period of about 41,000 years. So we will have, we're currently at 23.5 degrees, but we might be slightly less or slightly more than that. And then precession is the wobble in the axis. That's on the order of about 26,000 years. Both obliquity and precession impact the amount of light the different hemispheres will receive because it's about the tilt of the Earth. And these three types of cycles will impact climate on a large scale. And we have seen this in the past, we will see it in the future. So, when we look up into the night sky, what do we see? One of the things we see is how the phases of the moon, how does the moon change? So, Earth is rotating, the moon is rotating as well. The Earth is orbiting the sun, the moon is orbiting the Earth. Um, it turns out that the moon is actually rotating at basically the same rate as the Earth, so we always see the same side of the moon. The same side of the moon is always being presented to us. We don't see the far side of the moon. Um, the moon orbits around the so basically because of or the rotational period of the moon is such that it's always the same face facing the Earth no matter where it's at in its orbit. The moon will orbit the Earth in about a month. It's slightly less than a month, but it's about a month. And these are the phases of the moon. So we start off with the new moon. The new moon is when the moon is between the Earth and the sun. Okay, so the moon doesn't actually shine itself, it is just reflecting from light from the sun. So if the moon is between the Earth and the sun, all of that light is hitting the backside of the moon, and so the side facing the Earth is not getting any light. And so it's the new moon, there's no moon. We don't see anything. We then have a crescent moon, so that's a slice of the moon as the moon starts to move out of that direct alignment with the Earth. The Earth, it goes Earth, Moon, Sun. As it starts to move out of that alignment, we start to see a sliver of the moon appear. This is called a crescent. When it's starting to appear, it's waxing. When we get to the point where we can actually see half of the visible side of the moon, we call that first quarter. We call it a quarter because we're seeing half of a half. Then we continue rotating, so we're seeing more and more of the moon. Orbiting, we see more and more of the moon. Gibbons is when we are basically have only a crescent is not visible. So it's the opposite of crescent. And again, waxing is as we're getting closer to full. And then when the moon is on the opposite side of the Earth from the sun, that's the full moon. So we have the full amount of the sun's rays are hitting the moon, and we see all the moon. Then we go into the waning phase, so that we're seeing less of the moon, that we've gone past full, that we're heading back towards the new moon. So we go through gibbous, where we have essentially 3/4 is visible, or 3/4 of the half is visible. Then we'll get into the third quarter. It's called the third quarter because we have gone past the half into, again, a quarter. And then we'll have crescent, and then we'll get back to the new moon. Again, the moon rotation is synced to the Earth rotation, so we never see, quote, the dark side of the moon. And these are actual images of a crescent, third quarter, gibbous, and a full moon. The other thing that we can see with the Earth and the moon are eclipses. Eclipses are special instances where the moon, Earth, and sun align such that we either block some of the sun or we have shadows. So because of the relative distances and the relative sizes, it turns out that the moon and the sun appear to be approximately the same size from Earth. So that means that the moon can actually move completely over the sun and completely block the sun. So that's what's called a solar eclipse. So the moon moves in front of the sun and blocks it out. This can only happen in the new moon phase. Think about it. The only time that the moon is between the Earth and the sun is this new moon phase. So that's a solar eclipse. That's the one we normally think about. When we think about eclipses, these are the ones you can't look at it because you don't want to stare at the sun. It's not good. Everything goes dark for a little bit because we've blocked out all the light of the sun. A lunar eclipse is where the moon moves in Earth's shadow, and we are blocking sun's light. That basically the moon is, we have the shadow of the moon. And so we are going to be having, I'm sorry, this is not coming. All right, sorry about that. So a lunar eclipse, let me say this a little bit better, is when the moon moves into the Earth's shadow. So that means that the moon becomes dark because the Earth is blocking the sun's light. So this can only happen in the full moon phase. So again, if the Earth is blocking the sun's light from getting to the moon, that has to be in this full moon phase when the moon is on the opposite side of the Earth from the sun. So a solar eclipse, you're going to have the moon between the Earth and the sun. A lunar eclipse, you will have the Earth between the moon and the sun. So the lunar eclipses are perfectly fine to look at with your naked eye because you're not staring at the sun. They're not quite as impressive as the solar eclipses. And that is all of the material I wanted to cover in this first week. I am going to show you the video for week 1 introductory lab. So let's see here. It is on the metric system. So we will show this, and it's about 9 minutes. So I will take my headset off and hopefully you won't hear anything from me in the background.
Hello students, welcome back for another pre-lab video. This is Callan Bentley. This week in lab we're going to be taking a look at the metric system of measurement. We're going to practice taking some measurements of mass and distance and volume and even combining some of those to get new quantities such as density or specific gravity. And we're going to practice a little bit with the nature of scientific inquiry. So you're probably familiar with the fact that there are 2 major systems in the United States of America for measuring things. The one used by scientists is called the metric system, and that name, metric, is based on meters. The meter is a unit of distance in the metric system. So here, for example, is a full-grown man extending his arm. That's about 1 meter from his nose to his fingertip. A typical door is about 2 meters tall. A typical football field is 100 meters long. We also have a unit of volume. That's the liter. Typical can of soda is about 3/10 of a liter in size. A large soda bottle would be 2 liters in size. And if you're filling up the tank of your car, that's going to take about 68 liters of gasoline if it's around 18 gallons in your car. In terms of mass, we use grams. Paper clips are about 1 gram each. That's a good reference to keep in mind. Nickel is about 5 grams, a lemon 100 grams, and a typical laptop computer weighs about 1,000 grams or 1 kilogram. We've got the meter, the liter, and the gram here. Those are the top 3 in this chart. You can see that the metric system also includes some other units that are used to measure other quantities, such as temperature. Kelvin is used there. 1 Kelvin is the equivalent of 1 degree Celsius. Time is a familiar unit to all of us, the second. We can modify these base units by putting prefixes on them that mean that they are either larger or smaller than the base unit. Many examples of that are shown here on this table. You can see, for instance, that the prefix giga, represented by the symbol G, represents 1 billion times the base unit. And you may be familiar with that if you have a computer and you're used to talking about gigabytes of storage. Or megabytes of storage, that means 1 million times the base unit. You may have heard of kilobytes as well. That's a K, and it represents 1,000 times. So those are all quantities that are larger than the base unit. But you can also have quantities that are less than the base unit. And several of the ones that are most important here include centa, milli, and micro. A centimeter, for instance, is 1/100th of a meter. All right, so that's 1 over 100. 1 millimeter is 1/1000th of a meter, so 1 over 1,000. It's 10 times smaller than a centimeter, and so on. Now these quantities can be combined to create additional units. So for instance, if you want to talk about speed, you need to have a unit of distance compared to a unit of time. So you might represent that in meters per second. If you're talking about density, you are going to want to express that in terms of a unit of mass per unit of volume. And typically we express that in grams per cubic centimeter. So how many grams of mass does 1 cubic centimeter of a given substance weigh? And you might wonder about that cubic centimeter there as the unit of volume. Really, that's a unit of distance cubed, but a cubic centimeter is the equivalent of a milliliter. So really when we say grams per cubic centimeter, we're saying grams per milliliter. So how do we convert from one unit in the metric system to another unit in the metric system? It's really actually quite easy because each of these is a multiple of 10 relative to the ones above and below it. We can basically simply slide the decimal place over by an appropriate number of units. So, for instance, say we have this set of conversions. We need to convert 253 centimeters to some number of millimeters and some number of meters. We need to convert 4,566 grams to some number of kilograms, and we need to convert 3.7 liters to some number of milliliters. How do we do this? Well, it's pretty easy. So when you're converting from one metric unit to another one in the same class, for instance, from grams to kilograms or milligrams, or from meters to millimeters or kilometers, basically all you have to do is move the decimal place over. So the way this works is first figure out where your decimal place is. If there's not one obviously on the number, you have to add it, and it comes after the last digit of the number. And so say this is 37 grams, and we want to say how many milligrams that is. Basically, a milligram is 1/1000th of a gram. So as we're going down towards a smaller unit on this ladder, we want to move the decimal place over to the right. Milla means 1,000. There's 3 zeros on 1,000, so we move the decimal place over by 3 spaces, like this. 1, 2, 3. All right? And then we add in zeros to match. So 37 grams is the same as 37,000 milligrams. Now, let's say we want to make it larger, a larger unit. Those same 37 grams, how many kilograms is that? Well, we need to realize that a kilogram is 1,000 times larger than a gram, so the number is going to be smaller. And when we're going up the ladder, we move the decimal place over to the left. So again, 3 spaces are required. 1, 2, 3, add a 0 in for that third space. And now we understand that 37 grams is the same as 0.037 kilograms. This allows us to go ahead and take the example we looked at earlier and quickly work through these conversions within the metric system. 253 centimeters converted to millimeters and meters. That's pretty easy. We simply slide the decimal place over 1 space for millimeters because we're going from 1/100th of a meter to 1/1000th of a meter. And to go from centimeters up to meters, basically we slide it over to the left by 2 spaces. So we get 2.53 meters. Very similarly, converting grams to kilograms, we simply slide the decimal place over by 3 units, so 4,566 grams is the same as 4.566 kilograms, and 3.7 liters is the same as 3,700 milliliters. There are also conversions, however, that require us to go from metric to other systems of measurement, like the Old English system. So here what we need to use is we need to use the conversion factors that are listed inside the back cover of our lab manual. And using those, we simply do multiplication or division to convert from one to the other. So for instance, for 17 inches, there's 2.54 centimeters in an inch, so we multiply 17 by 2.54, and we get a new number, 43.18 centimeters. Going from pounds to grams, we use the conversion factor. We end up getting a very large number of grams, perhaps too large a number, and that might be better expressed in kilograms. We could also go from gallons to liters, or here we've got liters and we need to go to gallons. We've got 3.78 liters. There are 3.78 liters in a gallon, so the conversion here is 3.78 divided by 3.78, which gives you 1. Now for really big things and really small things, we use other units. So for instance, when we're out in space and measuring the distance between bodies in the solar system, we use the astronomical unit, where 1 astronomical unit is defined as the distance, the average distance anyhow, from the Earth to the Sun. And you can see that many of the other planets are very much further away from the Sun than the Earth is. For instance, Neptune is 30 astronomical units away from the Sun. That's 30 times further away from the Sun than Earth is. For really small stuff, we use micrometers. That's basically 1/1,000,000th of a meter, also called a micron for measuring distances, or a nanometer, which is 1/1000,000th of a meter. So that would be useful for measuring the sizes of, say, microscopic plankton like these coccolithophores. Finally, this week in lab, you'll be doing some experimentation, some hypothesis testing, which can be resolved by measuring certain quantities. You're given a graph in your lab manual where you're asked to measure the shoe length of various people in your class and compare it to their height. You'll be using millimeters for the shoe length and meters for the height. And you'll get a spread of data from the various people in your class, and then you're going to be asked to fit a trend line to that data so you can say overall how height relates to shoe length. Not everybody will fit along the trend line exactly. Some people are going to have relatively large feet for their height. Other people might have relatively small feet for their height. Okay, so I think that ought to give you a good introduction to the metric system and the act of measuring things as scientists do. Have fun this week in lab. I wish you the best of success.
Okay, so I do want to tell you we will be doing any sort of math we do, we'll use the metric system. So make sure that you pay attention to this. Don't just think it's, oh, I need it for just this week. We will be coming back to this. A hint I do want to give you is that when you're going between different units, think about which one's bigger, which one's littler. So if you are going from a big unit to a little unit, you will have more of the thing. So if you're going from a kilometer to a centimeter, you will have many, many centimeters in that kilometer. If you're going from a little thing to a big thing, so say you're going from a micrometer to a kilometer, you're not going to have many of the big things. So, if you're going from a little thing to a big thing, you're going to have very, very few of the big thing. So just think about that. Does this make sense? If I'm going from something that's small to big, would I expect to have more or less of the big thing? And then pay attention to what units it's asking you to do. So for that foot height thing, you are doing the feet in one unit and you're doing the height in a different unit. So make sure you're using the proper units. And I think that is all for this week one. Hopefully we're going to enjoy being in class together this term. And if you have questions, feel free to ask me.